Hello and welcome to Tools and Craft, the show where we talk with the engineers, inventors, and designers who shaped computing as we know it. I'm your host, Devin Zugel, and today we're talking with Louis Pouzin. Louis is the inventor of the datagram, a precursor of the TCPIP protocol, and he's the designer of an early packet switching network called cite. In the 1960s, Louis created the ancestor of the command line interface, and he coined the term shell. Currently, Louis is the director of projects at Eurolink, a lobbying organization working for multilingualism and better internet governance. Louis is also the president of Savoir Faire, which manages top-level domains for OpenRoute, an alternative DNS service challenging ICANN. So Louis, welcome. And thank you very much for being here. I've been really looking forward to this conversation. Can you start by talking about some of the problems that you've tackled in your career and what drew you to projects like cite, Eurolink, OpenRoute, and RENA?
Well, initially, my first job was in a telephone company because I knew nothing about industry. I just went to École Polytechnique, but most of my colleagues were people from reasonably I wouldn't say rich, but actually sufficiently involved in the Parisian society so that they knew all their parents usually had already jobs and so on. But I was coming from the countryside, so I knew nothing about that milieu. That's where I started. And after that, I joined a telephone company. And then someday I read an article about computers. The word computer didn't exist yet. So they were using electronic calculators. It seemed to me so attractive, something I know nothing about, but I think it was fantastic to have those machines doing extremely fast calculation. Machine Bull and IBM was the only two companies which was doing some kind of equipment which were not yet called computers, but they were doing mainly administrative calculations and using punch cards. But some of those machines had the possibility to have programs, but programs made of wires you would, plant on a board and make connection manually between those pieces of equipment. And one of my colleagues introduced me to Professor Corbato, who was an American working at MIT and who was heading a new team for time-sharing. Time-sharing was again a totally new concept of using machine simultaneously with several people. There were two other places in the US where they were also preparing for some time sharing, but much more limited because you had to use only one particular language. But while in Corbato's project, you could use the machine entirely for what it was built. I mean, you use a physical machine in order to use it with any language or any compiler you would like. So I was lucky to be introduced in that place, and I joined MIT Computing Center at the beginning of 1963. And several months later, I brought my wife and two kids. Engineers did not make programs. They was dedicated to lower level people called technicians. But quickly I started to use my own terms, making macro instructions, which they were not using. It allowed me to write faster the programs and also to make them more readable. I was aware of Lisp because I had read articles, but nobody was using Lisp except, there was a group. I think the head was McCarty. And he was one of the famous experts in creating Lisp and using Lisp. But it was a different department. In MIT, you have boxes with people who are doing quite different things, and they rarely discuss those things together. they don't discuss when they go to the cafeteria, but that's other subject, like going skiing, you know. I decided that I will not stay in the US, but return to France. So I didn't want to all my children becoming American because I would never be able to understand them. So I returned to France. And of course, since at that time, I was practically the only one in France who could speak about time sharing in English. So I was promoted in a way without making any effort as a sort of go-between between the American who were visiting and time sharing and things like that.
So before you were working on Cyclade in the 1960s, you spent your time at MIT. And can you expand a little bit on how did that period of time shape your thinking and the work that you did later on?
Well, actually, it was a major focal point for my life. Just learning English and computing would have taken me probably 10 more years in France, but it would not have worked at all because when I went to MIT, I was already 30. If I had waited for the time this knowledge could be acquired in France, it would have taken 10 more years. So I would have been 40. So if you start your career when you're 40, it's a bit late.
So can you talk a little bit about what the Cyclade project was and how you got involved?
Someday I got a call. I was at the time working for a car building, a car producer. It was Simca, which was a French company. I had been there for 1.5 years or something, not very long. And I quit them when I got the call I was going to be talking about. I was in a computing department, just producing documents for the people who were manufacturing cars. And that was extremely repetitive. Why were they calling me? It's because the French government at the time, it was General de Gaulle, and this man was a person who had a very strong sense of the French, I won't say superiority, but French independence. They wanted to have a control data computer because it was fast enough to calculate all the elements of a nuclear weapon. But the American had objected to that and didn't want to deliver the control data machine. So they had created a separate company which was supposed to do service bureau, but it was also computing the bomb. And so they needed some independence for computing. That's why they created CII, the beginning of ARPANET. It was very beginning, But it was very fashionable in the US to talk about that because it was the future. So they visited people who described all the many fantastic things you could do with a network of computers. The conclusion was that they had to develop something like that in France. So they called me and said, the government wants to develop a computer network linking all the administrations. I say, yes, well, okay. You want to go it? You want to do it? You say, well, why not? It was not many people who could do that in France at the time,
How did they find you?
Well, I had given conferences on time sharing, for coming back from the US. I was perhaps one of the unusual persons who could, having been in industry and also giving conferences in universities. Usually it was totally separate. But since I'd been in the US, the people in universities knew me, and the people who were in the group of people that the government had asked to think of how to be independent in computing, they knew me because I was known in the scientific and industrial part of France at the time. So they didn't have many people to decide about. It was a sort of independent agency, independent not from the government, of course, because it was created by the government, but independent of other ministry. So they had relatively more money than other ministries, and they were ready to go as long as they could find someone. So it was me.
What sorts of colleagues were you looking for when you started recruiting?
Engineers. At the time, there were mainly theoretical things they were dealing with, teaching things, but never implementing anything. Engineers were people who were trained to implement things, trained to ask questions, why this, why that, and so on, but not making conferences. So in a way, I trained those guys to make conferences because we had to do some propaganda about the project.
Who was the propaganda for, and who were you trying to convince about the project?
Mainly the people who have power and a minimum of understanding of industry. And that's needed when you want to build something in a country like France.
How did the architecture of Cyclades differ from ARPANET, which was happening around the same time?
Well, something were common. It differed considerably is that ARPANET was a single network first, which has a single namespace, and it was using physical addresses for where you send things. When people wanted to connect to the internet, they had to develop a special hardware within their own computer to be able to talk to ARPANET. That was a big mistake because very few could do that. So I decided to adopt standard protocol. Perhaps it could be less efficient than specific protocols built for ARPANET. But I think having specific protocols is always a nightmare,
It's sort of like having a USB, the universal serial bus. The word universal is there so that's a standard, and you don't end up having to get different dongles for every single thing.
So that's makes things much simpler, and also it can be implemented much faster also. And in a project like that, time is critical. If you don't go fast, then it's abandoned, So usually because people lose confidence in the way the project is managed, and they decided that it's getting too expensive, so whatever, And politics change, politics change often.
I come from an engineering background myself, and for the longest time I always thought, well, just build it, and if you build it well, then people will use it and they'll respect it. But right now I'm leading a project at work, and I am learning this lesson myself of you have to explain why it's important to people. Mm-hmm. You have to go find the right people, you have to convince them, and it's a continual process of telling the story about why you're doing it. Mm-hmm. And that's just as important as actually building it, because if you don't do that, you will lose the opportunity to keep building it.
That's right.
Yeah. Mm-hmm. So you mentioned that ARPANET had to create a direct channel between the two nodes of the network, and also another challenge was that it had a bunch of custom protocols that weren't standardized. Can you expand on that a bit?
Well, the fact we were doing Cyclades was as another component politically. It's to create in France an industry which could be competing with IBM or whatever, Mainly IBM because there was the major competitor at the time. Things should be extremely flexible in attaching things with each other. Therefore, standard protocol to begin with. Maybe not the best ones, but the best ones for the time it takes to implement. Why not let them go like a taxi cab, You send each piece of data with an address. That's all they need. It's like, when you take a taxi to come here, taxi has an address. We don't tell them which way they should take. So that means the piece of data can take whatever direction, which is at the moment open available, not saturated, even possibly taken several directions, and in the end, either they put together or if there are redundancy in the transmission, you drop the ones which arrive later than the first ones. So that was an idea which was already in the air at the moment. It had been proposed by Paul Baran. It had been studied in the context of military. That means they wanted to have something which could communicate no matter what the damage could have done to the network by the enemy. And it was roughly tailored for short messages which had to go through no matter what. Therefore, we have to make sure all the things will arrive at some point and put them in appropriate order. Well, that's no tricky things in computing. You just put numbers on it. When they arrive, you put them together. So the people who had not computing culture thought it was a terrible thing to do, put things together and so on. Because in their mentality, if you have A, B, and C arrive before B, we have to wait for and so on. But as long as they're all there, you can put them together. To me, it was relatively obvious to do that. It sounds a priori, it sounds stupid. Packets which have been partially transmitted, in excess, you just drop them. You say, well, but how do you make sure things arrive? If you have a lot of data to a small number of destination at high volume, then probably channels are a better solution. But if you have a lot of transmission relatively short, a few thousand characters, or maybe a few, something like a document, for example, which may be something like 200 pages, or it may be a short message. Well, each one will maybe cut into pieces, and they will arrive, the pieces, at some point.
Presumably the channel method would be better for something like video or like video chatting, right, where you want it to be more consistent, and it's more like a phone call.
Video is different. Mm-hmm. Because video, not only it has to be relatively constant for the person who look at the image, but also it has to have a regularity of delivering, which is not necessary when you transmit data. That's why usually video systems use buffers. They get enough of the image to be able to deliver it with regularity.
One of the things I was thinking as I was reading about Cyclade and the packet transfer network system that you put together as compared to the channel network is it feels like it's very anti-establishment and potentially threatening to the entrenched ways that the computer and telephony industries worked. Was that something that you intentionally designed into the system, or was that more of sort of an after effect? And I'm very curious to hear your thoughts about that, because it changed the way that people had control.
It changed the way, yeah. The easiest thing for ARPANET is that it was a single provider, a monopoly in a way. Mm-hmm. And that's what they thought of it. They wanted to do something which the whole world would use, because it would be under control by the U.S. government. Well, to me, it was a major flaw. In Europe, if you're thinking about a system which will need every country's approval, then you're dead. It's impossible. You have to have a system which is flexible enough so that each one can use it with a minimum effort without making complications. Each separate network can be managed in a different way.
It sounds like this flexibility was crucial for the internet to be able to scale, so that more people would be willing to be part of it. And the only thing that everyone had to agree on was that very thin protocol layer of just how to pass messages. And after that, everyone could make decisions on their own.
That's it. That was Cyclade. That was what DARPA has taken as a solution 10 years later. But they didn't change their strategy. They wanted to get the whole world into this network as fast as possible. so that there couldn't be any opposition to it. They almost succeeded, but not completely.
So the TCPIP protocol suite is nearly ubiquitous today. And considering that they were developed in the 1970s, this is impressively durable. Software tends to change very quickly, and creative destruction happens really fast in the software industry. So how have these systems held up over time, and what problems are they facing now? And how does the TCP/IP protocol suite not work for us so well today?
So that's a kind of thing which can't stay for many years, can't stay along for many years, because most companies require more, let's say, more quality of service. Quality of service is a number of terms like reliability, congestion, whatever. If you want to optimize the service, should that be done for some specific customers, or should that be done for the whole population, and so on? So at the moment, the management is still quite poor, not optimized at all, and people don't have any guarantee of quality of service. So that's not tolerable for things like, for example, if you get a surgeon operating a patient somewhere, you can't tolerate delays or, let's say, packet being disposed on later. So that's the kind of thing which has never been really taken as a principle.
Can you expand a little bit on who is responsible for that governance in our current system, and how you intend to change who's responsible for that governance?
You have to have different classes of service in which you offer a guarantee in terms of parameters, for example, private users, which pay more, which have priority on the lower user, and so on. It's like electricity. You pay depending on the charge of the level of electricity consumed within the network.
That's very interesting, especially the surgeon example. I think a lot of people talk about net neutrality, as here in the United States, at least, it's a very hot topic around how people in San Francisco tend to have the view that everybody should have the same service, and you shouldn't be able to pay to play. But the surgeon example, I think, is a very interesting and challenging one, because it does make sense. Like if I'm at home watching Netflix and someone else is getting open heart surgery, I think they have a little bit higher priority than than me watching Seinfeld for the fifth time.
Any urgency service may require to have priority over other ones.
Right. Just like how an emergency vehicle can drive through the road and they turn on the siren and they say, I have to go. Like who gets to decide whether or not that is the system that we have?
Well, at the moment, the people who can decide are the people who provide the networks.
The ISPs.
But they won't do it unless the customers require them.
Right. It's an alternative DNS service to challenge the ICANN monopoly. What problems arise from that sort of monopoly on top-level domains? Why is that a problem?
Well, first, if you talk about neutrality, I think it doesn't exist. It's a metallurgy. But it makes people more happy to think it exists.
What problems occupy your time these days? What have you been thinking about recently, and what have you been working on?
We developed OpenRoute initially so that the RENA system could communicate with each other without having a physical network. But for that, we needed to have a different protocol because it would be RENA to RENA. So that's, in a way, what OpenRoute is. It's a sort of platform which makes networks compatible with each other, which is not the case today. It's a matter of to understand the logic in the industry. Industry at the moment has developed a lot of things for the existing internet. But, so was electricity 100 years ago. And when you get all kind of innovation in electricity, they had to adjust to that. So we have to plan, in other words, to anticipate and to find solutions. For the moment, the network will have to change completely. It's not enough to have those functions in the network. The user also have to be able to adjust to that. Yeah. That's take much longer time than just changing the technical things.
How do you hope users use computers differently in the future? And how do you hope networks will evolve as we move forward into the next decade?
That's something which is a bit frightening. When I look at the street, everybody has people being somehow have adjusted to being able to walk in the street, to look at around, and simultaneously to play with a tablet. They lose a lot of capacity for making decisions, thinking, having no ideas, because they are completely suborned to. A lot of people think internet will be the same forever. Not realistic. They haven't thought yet that they will have to adjust to a new era of internet. We'll have a period of time to adjust to the limits of what can be done with computers and what should not be done by computers.